So last class, we talked about, the class on Monday actually, we talked about how TCP works. We looked at the TCP three-way handshake. There are two handshakes. One is for collection establishment and another for collection and termination. And we looked at the meaning of sequence number and acknowledge number. Basically, the sequence number will number each byte of data being transferred, except that it will also number the SYN packet and the FIN packet. And the acknowledgement number is the number of the next byte a party expects to receive. So today we're going to look at how we can manipulate TCP, how to attack TCP, inject TCP. Before that, we need to understand the state machine of TCP. So basically, TCP is a collection-oriented, different from IP and UDP. So there is a state machine the client, both the client and the server have to maintain. So this is a state machine looks like. In this figure, it draws the state machine for client and server. So we are going to look at the first half before how this is established using this example. So first, at the beginning of any collection, both client and the server, their TCP status or state is closed. So then the server will first request its operating system. The server process will request its operating system to sign a port number for me. Then the server will enter the state of listen. It is ready to listen to any remote collection request. Then the client will do the same thing. It will request a port number from its own operating system and send out a SYN packet to the server. So when the server receives this SYN packet, the server will enter this SYN received state. And the client will enter this SYN sent state. After that, the sender should reply a ACK message and also a SYN message. That's the second step in the three-way handshake. So after that, the server sends out this message to the client, and the client, because it receives the SYN and ACK message, it enters this established state. So it is ready to send out data or receive data. But at this moment, the server is not ready because the server sent out a SYN message, and the server has not get the ACK for that SYN message. So only if the client send out the ACK message again to the server also enters the established states. So after that, the server can receive and send data. So the interesting thing here is no matter which state you are in, when you receive a reset RST message, this collection will be terminated. So because when you receive a RST reset message means something is going wrong in this collection. So I'm supposed to terminate this collection. So this can be used for attacks. So let's look at the first attack. The first attack is SYN Flooding. So basically we have a client, we have a server, and the attacker in this case is a client. So the attacker can send out many collection requests. So basically it's just a SYN packet, as many as possible. And because the attacker can spoof its own IP address, so it doesn't this client doesn't have to use its own IP address. It can use a fake IP address. So when the client sends out a lot of SYN packet, the server will respond with a SYN ACK packet. And after server responds with a SYN ACK packet, it will waits for the ACK packet. However, the client will never send out the ACK packet. So the server in this case has to allocate a lot of resources for each request. It has to maintain the state machine. It has to prepare the buffer to receive data. So this could exhaust the resources at the server side. So in this kind of attack, it is very easy to pull off because the attacker doesn't have to guess the sequence number, because this is the first packet. It's going to send out the initial sequence number. There is no need to guess the sequence number. So SYN flooding is very easy to pull off, but it's also very easy to defend against. So when the server receives a SYN packet, it can say this is a half-opened handshake, or this is the first step of the three-way handshake, and the server can set some kind of timeout there if the timeout is short. So the server can deallocate those resources that was allocated for this SYN packet, this collection. So this is the first attack. So the second attack is a TCP Reset Attack. Like what we discussed before, no matter which state your collection is, collection or SYN received or SYN sent. So as long as you receive the reset packet, you are supposed to terminate this collection. So let's say if host B and host A, they already have an established TCP collection. Then now we have attacker host C. The host C will spoof host B, use host B's IP address, and it will set the reset field of the TCP segment and send this segment to host A. So when host A receives this segment, it believes it is host B who wants to terminate this collection. But actually it is a host C who is spoofing host B. So in order to pull off this, host C need to guess the valid sequence number and the valid acknowledgement number. So we are going to talk about two more attacks that also relies on a valid sequence and acknowledgement number, but this is possible. So in this attack, host C can terminate any collection between host B and host A. But we're going to say something more powerful. We want to spoof the TCP. We want to inject TCP data into an existing TCP collection. So remember that 1 week ago, we talked about rlogin. We discussed that rlogin is vulnerable because IP can be spoofed, but actually that time I only told you half of the story, because rlogin uses TCP. So spoof the IP address, the source IP address is not enough. You still need to spoof TCP. So let's see how it works. So first, we have a host A, and Alice has an account on this host A, and Alice wants to use host B to remotely log into host A. So it will use rlogin, Alice's username, and the host name, and also Alice's password. So if Alice does not want to specify the password, input the password every time, Alice can create a rhost file on this host A, which says host B is a trusted machine. So any collection from host B should be trusted, and I don't need to input password if I'm trying to log in host A remotely from host B. So, however, previously we said this can be done with IP spoofing, but that is just the first step of this attack, which is not enough. Let me explain why it's not enough. Let's say host C, in this case, it will, because this is a TCP collection, so host C will send out a TCP segment, and the first packet would be a SYN packet. So host C will set a SYN, and the sequence number, host C will generate its own random sequence number, and will give the spoof the source IP of host B. So host C will send this SYN packet to the rlogin daemon on host A. And when the rlogin daemon on host A receives this message, it replies back to host B instead of host C. So this response message will look like this. The SYN field is set. The ACK field is also set. The sequence number will be some random number generated by host A or the server. So in this case, we use initial sequence number server to denote it. Then the ACK number will be the sequence number host C used plus 1. And the destination IP address will be host B. So host C never gets this packet. But host C at this moment cannot send out any data. If it sends out any data, host A will not receive that data. Because at this moment, host A is not in the state of established. It's not established. So host A is still in the state of SYN received. It will refuse to receive any data before it receives the ACK message of this SYN message. But in order to send that ACK message, host C has to know the sequence number in the previous message. Because in that ACK message, the acknowledgement number is supposed to be the initial sequence number of the server plus 1. But at this moment, host C never gets this message. There is no way for host C to know what it should put in the acknowledgement number field. So that's why the IP spoofing was not enough. So in 1985, so Robert Morris, I think that time he was still a student. So he read the source code of the Unix kernel. He realized that the Unix kernel maintains a global initial sequence number. So all the process, whenever they want to send out, they want to initiate a TCP collection, they will use this global initial sequence number. And this global initial sequence number will change. It's not always a constant, but there is a pattern for it to change. So basically, it will increase by 64 after a collection is started. So whenever there is a new collection, it will add 64 to that global sequence number. So which means we can easily guess what is the global initial sequence number a process is going to use. So in this case, if host C still wants to spoof host B, it will first send out a legit packet. It will send out a SYN packet with its own sequence number. It doesn't matter what this number is. It's not important. And in this case, the source IP will use its own IP address. So after it sends out this SYN packet, host A will respond this with a SYN ACK. In this case, the SYN ACK will look like this. It will set the SYN field, set the ACK field, and it will have a initial sequence number from the server. And this number was actually taken from this global initial sequence number. And after the process rlogin took this number, this global initial sequence number will increase 64. So when host C gets this number, it doesn't need to reply. It doesn't need to send an ACK number. Then it starts spoofing. This time, it will use also a SYN packet. The sequence number, it will use another random number generated by host C. Doesn't matter what it is. Then it will spoof the source IP of host B. So in this case, host A will send out the ACK, SYN ACK packet back to host B. And in this case, the sequence number would be the original the previous initial sequence number plus 64. Even though host C never sees this message, but because Robert Morris looked at the Unix source code, so he knows, even though he never gets this message, he knows the sequence number will be this number. Then it can construct an ACK message with ACK field set with the previous sequence number plus 1, I guess. It should be the original sequence number. It doesn't matter. So the ACK number in this case, it will put the sequence number in this package plus 1. So here should be 65. So in this case, when host A receives this ACK message, the host A will enter the state of establishment. So host A is ready to receive any data. Then host C can send out a command to the rlogin process to remotely execute arbitrary command on host A. Any question?
So they wouldn't receive any feedback.
No.
Just have to go on.
This is a write only. Yeah. But still, even though you cannot receive any feedback from this connection, you can do something very smart, because you can run arbitrary command here. So that command can create another collection, like a reverse share, to collect back to host C. So normally that is what we do. Okay. So even though for this collection we cannot get that, but we can use that as a springboard to do something more dangerous.
Is there any way to do this nowadays? Can we predict sequence numbers still?
Yeah, it seems like you would.
Yes, we can still do something like this. But there is something more powerful we are going to discuss next. So in this one, we are not injecting data to any established collection. So next one, we are going to see how we can inject data to establish the collection. So basically, the root cause for what is happening here is the sequence number is not really random. It can be easily guessed. So after this, after 1985, the TCP IP standard, they changed. You have to use random sequence number to make this safe. So another much more powerful attack is called a TCP session hijacking attack. It is also called a TCP injection. So basically, the idea is similar to what we did before. You still only have a write-only channel to the victim, but in this case, we assume there is already an established collection between the two victims, host B and host A. So in order to pull this off, same as what we did just now, you need to spoof IP address, and you need to guess the valid sequence or acknowledgement number. So spoof the IP address is very simple. However, get the valid sequence and the acknowledge number is relatively difficult, because after the previous attack, right now the sequence numbers, they are random. So in this attack, host B and host A already has an established TCP collection. And the host C, which is the attacker, wants to inject some data to host A or to host B, maybe both directions. So if we only consider this one direction, it has to spoof host B's IP address and also get the valid sequence number and acknowledgement number. So this can be done easily if the attacker sits on the data path between the communicating two parties. So because if it sits on the data path, it sees all your packets. So it knows what is the valid sequence number, what is the valid acknowledgement number. So who usually sits on the data path between you and the website you are talking with? Router. Who's router? The IRP, ISP, Internet Service Provider's router. Your Internet Service Provider's router. Also, the website you are trying to talk to, its Internet Service Provider's router. So anyone in the between. So we cannot really trust them. So this actually happens. So this is a screenshot I took from, I think it's 2013 Black Hat. So Black Hat is the biggest hacking meeting in the world right now. So in 2013, someone did some research to say, does ISP, they inject our TCP collection? So what they find out is they do. So this is a page I took from their slides. You can, it's not very clear, but the IP, the domain name is apple.com. So when you visit apple.com using your browser, there is a raw advertisement injected here. You can view this advertisement. So who is doing this? Is your ISP. It knows your valid sequence number, valid acknowledgement number. It injects some data in your HTTP collection. So ISP can do that, but not only an ISP can do that. So actually anyone who can guess the valid sequence number or valid acknowledgement number can do this. And they do not have to sit on your data path. So another kind of a very hot area right now is called off-path TCP session hijacking attack. So in this attack model, host C, in this case is the attacker, doesn't have to sit on the path. So host B and host A, there is already an established TCP collection. The host C can somehow install an unprivileged app on host A. That's very easy to do. Imagine host A is your Android phone. You download a lot of apps every day or your iPhone. You download a lot of apps every day, and do you really trust those apps? You don't know what they do. And those apps, they don't have to be privileged. So those apps, you can infer the sequence number and acknowledge number of an established collection between host A and host B, using some bugs in the kernel. So the root cause here is still, so technically any app running on your host, on your phone, is not supposed to know the sequence number or acknowledgement number of any other collection from your computer to any other computer. But there are bugs in our operating systems. And using those bugs, they can infer what is the valid sequence number and acknowledgement number. So this app, after it gets the valid number, it will send back those numbers to the attacker. Then attacker can construct a spoofing TCP segment with the source IP of host B and the valid sequence number and valid acknowledgement number to inject data into this TCP session. So this is an idea published like 3-4 years ago. And this year, there is another idea. I think published this year. They showed a demo this year. I'm going to show you the demo, the video later in a moment. So basically, some researchers in UC Riverside, they find out that I don't even need to install any application on host A, which is a victim in this case. So as an attacker, I can probe host A by sending a lot of messages. So by using some side channel information, I can infer the valid sequence number and valid acknowledgement number of an established collection. So not the sequence number of my collection, because that's open to me. But somehow I can infer the sequence number of established collection. So as long as I can infer that sequence number and acknowledgement number, I can inject data and spoof host B. So I have a video to show you. Oops. So this is done by UC Riverside. So this is an attacker. This is, let me explain, this is too fast. So this is an attacker. This is the victim. So the victim is using a browser to visit a website, which is USA Today. And the attacker is not on the data path between US Today and this browser. It's not there. So the attacker tries to establish a regular collections to this user. So talking to other process on this host, basically. But the goal is to infer the validate the sequence number and validate the acknowledgement number between this browser and this website. So attacker establish collections. So you need to synchronize time between attacker and the server. And it's doing a lot of probing here. It guesses the source port number range and do a lot of probing. I think they get the port number. Then they try to guess the window size. So you don't have to get the exact sequence number or acknowledgement number as long as you fall into that window. So they're trying to guess what is the window range. Still doing a lot of probing here. Okay, they got the receive window size. They may also need to get the send window size. Oh, okay. Then we want to get the ACK number. This is all off paths. Just sending a lot of probe TCP message. So they're trying to get the sequence number, get the valid sequence number. Okay, after they get the sequence number, acknowledgement number, and also the valid window size, they start injecting some JavaScript. So in this case, they successfully injected some JavaScript. So as a victim, you still believe you are visiting USA Today. But actually your collection, your browser's connection to the USA Today's web server has been hijacked. An attacker off the path is sending out malicious data to you. But you don't know that. Imagine this could be any website. It could be your Chase. It could be your Social Security, whatever, tax. So this is why this is very powerful. So this is actually demoed this year, March, I guess. So the professor is from UC Riverside. Yeah, any question?
Yeah, what kind of message? You said the attackers are sending out some TCP messages. What kind of messages are these? Just like, are they like sync?
Actually, I'm not sure. I didn't read that paper.
Okay.
So basically what I know is previously, 2-3 years ago, what they did is they use, sorry. We got a lot of spams these days. So 2-3 years ago, so basically the goal is to calculate the sequence number and ACK number. As long as you have that, the spoofing the IP source IP address, that's the easy part. So previously what they started is I can install some malware on the victim. And that malware can make a lot of queries to the kernel to infer the sequence number and the ACK number.
Is installing a malware easy?
Yes. Because it's hard to define what is malware. That malware doesn't have to be anything malicious, actually. It just do a lot of queries to get those numbers. But in this paper, I'm not sure if this is published. They demoed this recently. I'm not sure if it's published. So in this work, they're showing is I don't need to install any app on the victim's machine. I can just send out some messages to the victim, and based on some side channels, I can guess what we need. Validate the sequence number and the ACK number for any established connection. So in this one, they didn't install anything there. So the interesting thing here is if you can see the domain name here is 3w.ustoday.com. So they are using HTTP. They're not using HTTPS. So if we are using HTTPS, the attack will be much harder because it's not only about spoof the IP address, get valid the sequence and ACK number. You also need to know the communication key because the communication is encrypted. If you do not have the key, whenever you inject something, the browser side they cannot correctly decrypt that. So that's why still those attacks right now they can be only pulled off for HTTP, not HTTPS. So that's why the next week we are going to talk about HTTPS. Basically, we are going to talk about transport layer security. So previously we started the IP and we started the IPsec. So now we started the transport layer, and we are going to talk about transport layer security. And HTTP is just HTTP over TLS. So we're going to talk about that next week. I will send you guys this video link later so you can take a look.